Okay, so let's begin. Again, I'm working from the AB multiple choice practice test, which if you're coming in from BC, is not in your packet, but you can access it through the AP on your BC review page under 5.9, under today's date. But there's some overlap, but it's also a little bit different as well. So as you turn your packets, I do encourage you to, if you have time, to go through the review page. So look through the summary sheet on page 1 and 2. For the BC students, you have a little bit more for your summary. And then I try to put the derivative and integral rules on separate blank sheets, as well as the most important rules and formulas and concepts over the course of our year on page 5 and 6. And then I have keys for those pages as well. Okay, so we're going to turn to page 7, your AB packet. And I think I'm going to try to work through every problem here. So section A is non-calculator. Now on your current AP exam, this is an older test from 2016, but I think shortly after, maybe starting 2017, 2018, they changed it to be 30 multiple choice non-calculator and then 15 calculator multiple choice. Here is 28 and 17. It's still the same number of multiple choice questions. They just kind of adjusted the numbers a little bit, but so that's why it has 28 for this particular year. Okay, so page 7. And again, if you have any questions, you can feel free to unmute yourself, or you can type it in the chat box and I'll try to check it fairly frequently so that I can hopefully answer your questions when I see it. All right, so starting with number 1. If y equals cosine 2x, then dy dx equals. So we have a rule for cosine. Cosine's derivative is negative sine of u times u prime. But we have to remind ourselves, okay, there's chain rule that is going to be involved here. So if we recognize our u value to be 2x, then cosine's derivative is simply negative sine of 2x times 2. Answer choice A. Okay, number 2. Definite integral or indefinite integral of x squared times x cubed minus 1 to the 10th. We have to understand that this is one connected problem. We can't separate this and say, okay, I'll do power rule here, I'll do power rule here. And for a complicated integral problem, we typically, if we can't expand, then we're looking at u substitution. We don't want to try anything like product rule or anything like that. That's for derivatives, right? So for integrals, we want to go through, in this case, u substitution. If we see a set of parentheses with multiple terms inside an exponent that is hard to expand through, then we do want to go through our u substitution steps. So we target our u value to be the portion inside the parentheses. And so our u value is x cubed minus 1. And once we identify that u value, then we're off to building the derivative information. Okay, so u equals x cubed minus 1. Derivative is 3x squared. Cross multiply, we get 3x squared dx equals to u. Solve for dx, and we get du over 3x squared. Okay, we put these back into our integral, replace the parentheses, or replace the parentheses with u, replace dx with du over 3x squared. And we know this is going to work out nicely because our x squared will cancel out. However, we don't want to lose track of that 3, so push that 3 out as 1/3. Now we have a nice clean integral rule that we can use with power rule. So u to the 10th is what we're trying to evaluate the integral for. U to the 10th becomes u to the 11th over 11. So we drop the integral notation, we drop the du notation, we have our antiderivative, and now we're just trying to clean this up. Okay. Replace the u back in terms of x. Well, I multiplied through first, and then I replaced it back in terms of x plus c. Answer choice D. All right, next up, number 3, page 8. Limit as x approaches infinity. So whenever I see infinity, I'm always thinking, okay, we're not going to plug anything in. We could go through L'Hopital's rule, but I find it easier if we're approaching infinity just to compare degrees and then use the what we find from comparing degrees to determine what the limit is. So here we're comparing degrees between numerator and denominator. And the highest degree that we see is x to the 4th. However, that x to the 4th in the numerator is under the square root. So really the overall degree is really x squared. Denominator is also x squared. And because we have the same degree, we know we can take the ratio of the coefficients. So that root 9 is the ratio coefficient of that overall x squared. And denominator is going to be 4. So root 9 over 4 is same thing as 3 over 4. So that's our limit. All right, next up, number 4. Page 8. If y is equal to parentheses x over x plus 1 to the 5th, then dy dx equals. So we see, again, too many things going on inside. Exponent is hard to expand. We're thinking about chain rule here. So chain rule, where we have to think about the outside component and the inside component. So the outside, we can go through power rule. The inside portion, notice numerator and denominator, so we're going to have to step through quotient rule to get to that inside portion. All right, so outside first, parentheses to the fifth becomes 5 parentheses to the fourth. And well, after we do that, we want to keep everything inside unchanged. Times the inside's derivative. So inside's derivative, we said we ought to go through quotient rule. So in a separate space, we have to build out quotient rule just to handle the derivative of this component. So f prime g minus fg prime all over g squared. F prime, x becomes 1. G stays as x plus 1. Back to f, g prime, x plus 1's derivative is just 1, all over g squared. All right, continue cleaning up. We have the derivative. We just have to algebraically get this to work towards one of the options that we see above. So careful when you're cleaning up quotient rule that you're not canceling things out between numerator and denominator, right? That minus is causing these terms to not really be suitable for reducing. What you want to do is you want to spend the time to just clean up the numerator. So distribute the 1 through and then combine like terms, and then you can usually with quotient rule, we're not going to do much with the denominator. The denominator is usually going to be is going to stay until the end of the problem. It's usually just the numerator that needs to be cleaned up within its own region. So here, x minus x becomes 1, so or x minus x becomes 0, and then only 1 is left over. So if I kind of break the numerator and denominator into individual parts here, I can think of it as, okay, the numerator is just x to the fourth, the denominator is its own x plus 1 to the fourth, and then there's a 1, and then there's a x plus 1 squared. Sometimes we forget that the 4 is not only impacting the x, the 4 is also impacting the denominator portion. So so we want to make sure that that we include that 4 in the denominator as well. So now these are just the same base. I could just multiply these two bases by adding exponents. Answer choice D. Continuing on page 8. Number 5, water is flowing into a tank at a rate of R of T, where R of T is measured in gallons per minute and T is measured in minutes. The tank contains 15 gallons of water at time T equals 0. Yeah, that's important information here. Values of R of T for selected values of T are given in the table above. Using trapezoid approximation, trapezoid sum, with 3 subintervals, as indicated by the table, what is the approximation of the number of gallons of water in the tank at time T equals 9? So I like to think in terms of, okay, so the accumulation of water into the tank, we can use trapezoid approximation. However, there's already water to begin with before we begin this accumulation of water, additional water into the tank. So we have to think about 2 things here. So if I want to find the water 9 hours in, I need to consider how much water there is to begin with, and then the accumulation over that 9-hour period. Okay, so essentially, it's this final equals initial plus displacement that we tend to use quite a bit. So y of 0 is just going to be 15. Our work is really trying to figure out using trapezoid approximation, what's the area under these rates, which will give us the amount of water that has been added in that 9-hour period. So off to the side here, we know that we're going to be adding up these areas of trapezoids. If I subtract the t-values, I get the width of these trapezoids that I want to find the area for. And remember, trapezoid area formula is 1/2 width, height 1 plus height 2. So we know the integral from 0 to 9 of r of t dt can be thought of as adding 3 trapezoids together. So 1/2 times width times 4, 9 plus 6. And then second trapezoid, 1/2 times 3, 6 plus 4. And then 1/2 times 2, 4 plus 3. All right, it's a little bit annoying that this is in the non-calculator section, so we have to work this out by hand. Oops, sorry. Not dividing, multiplying. Ten divided by 2 is 5, 5 times 3 is 15. So we have 15 gallons of water to begin with. In the 9-hour period, we've accumulated another 52 gallons. And so answer choice C. Number 6, the slope of the line tangent to the graph of y equals natural log of 1 minus x at x equals -1 is. So here we're just finding the derivative and evaluating the derivative at that point. So if we understand, okay, the rule for natural log is u prime over u. So we simply find the derivative. My u value is the 1 minus x, u prime over u, so -1 over 1 minus x. Once I have my derivative, plug -1 in, and I get my slope, and the slope is my answer. All right, number 7. Page 9. For which of the following pairs of functions f and g is the limit as x approaches infinite of f over g infinite? So again, we like to, if we're putting one over each other, if we're going to infinity, we're looking at comparing degrees. And if we want an infinite limit, typically that's going to mean that we want our numerator degree to be growing at a faster rate than your denominator degree, okay? Because we want the fraction to get larger and larger. So if we look at option A, f over g x squared plus 2x divided by x squared plus natural log of x. The highest degree will be x squared. Natural log grows at a slower rate than polynomial, so we can ignore that natural log of x. So the highest degree is x squared, x squared. The limit is equal to 1. We take the ratio of the coefficients, so answer choice A is not going to give us that infinite limit we're looking for. Answer choice B, f over g, my denominator has a higher degree, and because my denominator has a higher degree, we know this denominator is getting larger at a faster rate than the numerator, and so this fraction is getting smaller and smaller until it heads towards 0. Answer choice C, limit as x approaches infinity, you have 3 to the x over x cubed. So it's good to know these comparative growth rates where between different families of functions, they can grow at predictable rates if we're comparing them over each other. So typically, this only works if we're going to infinity. But if we're going towards infinity, natural log is going to be the slowest growing function, and then followed by radical, followed by polynomial like x squared or x cubed, and followed by exponential like 2 to the x. So if we have one type over the other, typically if we're going to infinity, it's either going to be 0 or infinity, depending on which side is growing at a faster rate. So in this case, my exponential is growing at a faster rate than my algebraic or my polynomial. And so therefore, if my numerator is the one that's growing faster, then that will push my limit out to infinity. Answer choice D, my highest degree is e to the x, and so I can ignore the x cubed and x squared. The ratio ends up being 3 over 2, which is not infinity. And then answer choice E, both numerator and denominator are under the same family of functions, so we just take the ratio of the coefficients 3 over 2, which is also not infinity. Right. Continuing on page 9. We have a definite integral now. We have bounds involved. And so we're looking, okay, what can we do to because right now there's no rule that can handle such a complicated problem, but maybe u substitution can do it. So if we look ahead, maybe if our u value can be what's inside the radical, and if we explore that potential u value, we want to just look ahead. Are we able to predict that that it will match up with our remaining x's? And it will, because if our u value is x squared plus 9, the derivative will become 2x, and 2x and x will pair up nicely to get rid of that x. So the whole idea with u substitution is we're trying to create a simpler version of our original problem, and we would like the x's to go away. We want our new variable u to be the only thing that remains, and that's a good indication that that we're going down the right path, and then our u substitution method is the appropriate method. Okay, we're able to get the x's to pair up and cancel out for us. So now we're looking, okay, what can we do with that? There's a 2 in the denominator, which we can push out as 1/2. We do have a simpler version of the problem, but we have to recognize, okay, just because we see a u in the denominator doesn't mean that it's a natural log problem. We only do natural log if it's u to the first power in the denominator. If it's any other power, we have to bring it up and make it go through power rule. So now that we are in the numerator, ready for power rule here. So add 1 to the exponent divided by the new exponent. Sorry, no plus c here. We have balance involved. Okay, so dividing by 1/2 is the same thing as multiplying by 1/2. Sorry, multiplying by 2. Twos cancel out. We have our u. We're ready to involve the bounds, but right now there's a mismatch of variables. We want to bring this back in terms of the variable that we're working with. So let's bring back our x variable. Let's bring back x squared plus 9 and make it to the 1/2. Okay, let's involve the upper minus lower bound. So upper bound first, 4 in for x, minus, now lower bound, 0 in for x. Okay, so 4 squared plus 9, that's 16 plus 9, root 25. Minus root 9. So that gets us 5 minus 3, which is 2. Number 9, page 9. Let the function with derivative given by f prime. So f prime function is given to us. On what interval is f decreasing? So typically, when we're talking about decreasing, we're thinking about slope. So we would like to create an f prime sign line. And look at the arrows, whether our graph is rising or falling. Typically, we have to find the derivative to get to f prime, but if you look, this is already f prime, so we're already at the level that we want to build the sign line. So from here, we can just find our critical points, go directly into populating our sign line. There's no need to find our derivative. So let's find our critical points. So that means we're going to set the numerator and denominator equal to 0. We want to look at look for critical points in both locations. It doesn't mean that we're going to find them in both, but we have to at least look. So here, I'm going to get a critical point of 0, divide both sides by -2. Here, if I take the square roots, I get 1 plus x squared is equal to 0. X squared equals -1. Take the square root, and we can't take the square root of negative numbers, so there's no critical point. There's no real answer. There's no real solution there. So no, the only critical point that we have is going to be at 0. So for our f prime sign line, choose values on either side. Let me choose -1 into f prime. Denominator is always positive because it's getting squared. My numerator, -2 times -1, is positive, so my graph is rising in this interval. If I plug 1 in, denominator is always positive. Numerator, -2 times 1 is negative. Negative or positive is negative. So here, my f of x is going to be decreasing on this interval from 0 to infinity. All right, page 10. Integral of e to the x plus e. Really, these are two separate terms. They're each going to have their own rule. There's no need for use substitution here since e to the x can just be its own integral rule, and then e to the first power. Understand this is just really just a numeric value, just a constant. So first we have e to the x dx, which we know is just e to the x plus c. E to the u becomes e to the u plus c. There's no need for u substitution. That's just an x. If you went through u substitution, the derivative would just become 1. So there's not going to be any leftover coefficients there. So e to the x is just e to the x. And then e, it's like the integral of like 2, right? 2 becomes 2x. 3 becomes 3x. E is just a number, so e becomes ex. Page 10. Number 11, the graph of the function f is shown in the figure above. Which of the following could be the graph of f prime, the derivative of f? So this is the f of x graph, and we're asking about the derivative. So that means we want a graph where the slope, the relative min is at -1 and the relative max is at 1. So I just want to create a slope sign line just to kind of match. Typically, we're given f prime and we're having to interpret it. But here, if this is the graph of f, then whatever you see is what you get here. So I'm just going to label this just so I can have some target numbers to look at. Let me say there's a relative min at -1. And let me say there's a relative max at 1. In the graph, this is the f of x graph, so whatever I see is exactly how I can interpret it. So decreasing, increasing, decreasing. But if I'm trying to get an f prime graph out of this, then I want to put it into a graph where the y-axis now represents slope and no longer location. So I want f prime graph where slope of 0 is occurring at -1 and 1. Okay. And to the left of -1, I want my f prime to be below the x-axis. So it's going to have to connect to that point. That's my anchor point, so I know it has to connect there. And then between -1 and 1, I want my f prime graph to be above the x-axis, so it has to go up and come down because there's a point waiting for us. And then to the right of 1, I want my f prime to be below the x-axis because negative. So that's going to match up best with answer choice B. Page 11, number 12. Between 0 and 1, what is the area of the region enclosed by the graph of y equals 0, y equals 1 over x, and x equals 1? So understand that this rational function, y equals 1 over x, kind of has this shape about it. We know c is going to be some x value between 0 and 1, so we don't know what that value is, but we can just go ahead and cut something off here and call that c. And then we're going to go to 1 because that's the right endpoint. And we know we're above the x-axis and below the curve. Okay, so it's asking, okay, what would represent the area of that region in terms of c, right? So we'll just go through our process of area. We know area formula is integral of top graph minus bottom. So let me draw a representative rectangle. My bounds are from c to 1. Top function is the natural log of x. Bottom function is the 0. The 0 can just drop out. So, sorry, not natural log. I jumped the gun here. It's the function is 1 over x, and then the integral is natural log. All right, so the top of my shader region is the 1 over x. The bottom is the y equals 0, so top minus bottom, 1 over x minus 0. I can drop the 0 here, and we know 1 over x is the same thing as 1 over u du, which is natural log. Once we find our antiderivative, we can evaluate between upper and lower bound. Upper bound is 1. Lower bound is natural log of c. So we know natural log of 1 is 0. Well, first off, this, if this pre-response, this would have been acceptable, but we have to somehow arrange this a little differently so that we can create something equivalent to this so that it can match one of the answer choices that they are providing us. So one way to clean up is natural log of 1 is equal to 0. So I can take that away. So I'm left with negative natural log of c. And the issue is I don't see negative natural log of c. So how else can I write this answer negative natural log of c? One thing we can do is we can think of in terms of log properties. Log properties, one of them is allowing that coefficient to come up as an exponent. So we can put that negative up as an exponent raised to the -1. So this becomes natural log of c to the -1. And then how else can I represent c to -1? C to -1 is the same thing as 1 over c. So I can write it this way. So this is probably the way that we're going to be getting to and having to play with these log properties in a way that can get us to the answer choice that will that they're providing us. Okay, we have asking about the derivative of these two terms, of the sum of these two terms. We haven't spent a whole lot of time reviewing arc-trig rules just because arc-trig derivatives tend to not show up that much on the AP exam. But if they do show up, typically it's going to be the tangent that's going to be the most likely one to show up. Now, technically, all the derivative rules are fair game for them, but some of the patterns that we see is that they tend to not involve the more obscure rules. So arctangent is the one that is the most common one amongst the arc-trig rules that have shown up. So as a reminder, the rule for arctangent is u prime over 1 plus u squared. So let me just rewrite the problem and also get this second term to get ready for power rule. Okay, so inverse tangent becomes u prime over 1 plus u squared. So my u is x, so 1 over 1 plus x squared. And then power rule for that 2x to the 1/2. Bring the 1/2 down, subtract 1 from the exponent. Twos cancel out. X to the 1/2, the same, x to the negative 1/2 is the same thing as x to the 1/2 in the denominator. So answer choice E. All right, next up, 14. If y equals f of x is a solution to the differential equation with the initial condition of order pair 0, 2, which the following is true. So we're going to be solving this differential equation. Take the integral of both sides once we get our full separation of variables. So I like to line up my diagonals so I can cross multiply. We can take the antiderivative. 1 dy becomes y. The issue, this is not your standard solving differential equations because the answer choice doesn't go past the integral component. So what we need to do is we need to, well, first off, the reason that they're not going any further is because if we went through u substitution, that x squared is going to be leaving us with something that we're unable to do by hand. And so we only have to get as far as we need to according to these answer choices. So we have to essentially evaluate our bounds from 0 until x. Right? If we were to go through that full process, it's the same thing as evaluating this in terms of x. So they are leaving this in terms of t here. I know it seems a little bit strange, but we understand that the integral of this will produce the same thing as, because we just aren't able to go any further, and the answer choice doesn't go as far as that. So what we can do though is we can play around with this order pair and actually solve for c at this stage, because if I plug 0 in for x, that'll wipe this whole thing out, because from 0 to 0, it'll just be it'll be 0, and I can just plug in at this stage and then solve for c. Now I can just take this and replace the c with 2. Now give me answer choice D. Yeah, a little bit of a strange one. Typically not the type of problems that we're accustomed to. All right, 12a, page 12. Function f gives the rates of evaporation of water in liters per hour from a pond where t is measured in hours since noon. Which of the following gives the meaning of the integral of 4 to 10 in the context described? So f of t is the rate of water evaporation. So we know if we're talking about a rate, then if we accumulate that rate over a period of time, then we're talking about something in terms of the amount of water. So we know first theorem can allow us to transform that lowercase f into uppercase f. And if lowercase f means rate of water evaporation in terms of liters per hour, then the antiderivative is going to bring us up to something in terms of the amount of water in terms of liters. So if we evaluate this, uppercase f of 10 minus uppercase f of 4, what does that mean? That will be the difference of water evaporated between these two time periods. So the total volume of water in liters that evaporates from the pond between 4 and 10 p.m. Notice your units have to change. So anything that involves liters per hour, that's going to be out. So you're really just deciding between A and B. A is a little bit off because it's not the first 10 hours. If it were first 10 hours, we would have to evaluate from 0 to 10, but we're only going to go from 4 to 10. So it's just how much has evaporated in that time period between 4 and 10. Okay, number 16. The first derivative is given as f prime, or the x-coordinates of the points of inflection in the graph of f. So we know points of inflection is working our way to the second derivative. So here are the steps we're going to do. We're going to find f double prime, find critical points, Now, once we find critical points, we got to go one step further. We have to make sure that we create our f double prime sign line. There has to be a change in signs in order for us to call this critical point a point of inflection. So some students want to just stop here. They solve for x and they feel like they're at the end of the problem. But if it's a point of inflection, we have to go through the sign line and actually consider, is the sign changing on either side of that critical point? So let's find f double prime. So power rule, 3x to the fourth becomes 12x cubed. 12x cubed becomes 36x squared. And set your second derivative equal to 0. Factor out the 12x squared. Solve for x, and we get 0 and 3. So you can see that there's an answer choice kind of teasing us that maybe this is the right answer choice, and some students want to just stop here and just pick that answer choice D, which could be this right solution, but we don't know yet, not until we get that second derivative sign line to tell us if the behavior on either side of these critical points is what we're hoping for. So that means take the additional step here, make your second derivative sign line. Now let's test points in each subinterval. So I'll test -1, I'll test 1, I'll test 4. All back into f double prime. So -1n for x, positive, -1n for x here, negative, positive, negative is negative. That's concave down. Okay, plug 1 in, positive. 1 minus 3 is negative, so positive times negative is still negative. Now notice that there is no change in sign, which means there's not a point of inflection at 0. All right, plug 3 in, positive. Sorry, plug 4 in, my bad. Positive times positive, which is positive. So there is a change in sign at 3, point of inflection at x equals 3. Answer choice A. Seventeen. Let f be the function defined by y equals 1 over x. What is the average value? So average value, we should be connecting that with average value theorem. Now, once we identify that formula for average value theorem, we're just making our substitution, replace our a's and b's with 4 and 6, replace our f of x with 1 over x. Now we can just continue working through this problem here. Okay, so 1 over 6 minus 4 becomes 1/2. Integral of 1 over x is natural log. Upper bound minus lower bound. 1/2 natural log of 6 minus natural log of 1/2 natural log of 4. And here you can see your answer choice doesn't quite match what we have here. So anytime we see natural log, we know there's that possibility of condensing using log properties in a way that is how sometimes they want to be presenting their answer. So there's a property that says natural log of a minus natural log of b is equal to natural log of a over b. This is quotient property. So now I can factor that 1/2 out. And then natural log of 6 minus natural log of 4 is natural log of 6 over 4, which is 3/2. All right, 13, page 13, number 18. The points 3, 0, x 0, x to the 1 over x squared, and 3, 1 over x squared are vertices of a rectangle. What value of f does the rectangle have a maximum area? So here it's rare, but we have a problem here involving optimization. So optimization is really a word problem form of finding critical points, right? So we just have to find critical points. However, algebraically, we have to create an area equation before we can find critical points. So let's figure out, okay, how can I create an area formula or area definition for this problem, and then I can find my critical points from there. So area of a rectangle is base times height, right? So my base is going to be the difference between 3 and x, which is just x minus 3. And then the height is just going to be the difference of my y value, 1 over x squared minus 0, or just 1 over x squared. And then if I can create that area equation or clean up that area equation and just work on the derivative, distribute that x through. So my area, if I want to get it ready for power rule, it's just going to be 1 over x minus 3 over x squared. I'm going to keep going here. So I have my area function. I'm going to find a prime. And really, you're just finding critical points, right? So you're always going to set your derivative equal to 0. And whatever you find is going to be where your solution is. So I'm just trying to figure out how to solve for x here. Bring everything over to one side. Solve for x. I get x equals 0, x equals 6. 0 is not going to make sense because we know x is to the right of 3, so it's got to be a positive number more than 3, and so only 6 will make sense. What are all the values of x for which the definite integral is equal to 0? So we'll find the antiderivative, set equal to 0, and then we can algebraically solve for x. 16 over 4 is 4. Set them equal to each other, cross multiply. Take the square root of both sides, or the fourth root of both sides. So fourth root is asking, okay, what four of the same numbers multiplied together can get us 16? And I'll get 2, so plus or minus 2. Page 13, number 20. Let h be the function defined by h of x equals the depth integral of sine squared t. Which of the following is an equation for the line tangent to the graph where x is equal to pi over 4? So tangent line equation, we need order pair, we need slope. So point means I'm just going to plug pi over 4 into the x of my h of x function. So the nice thing about this is the bounds are matching, so it doesn't matter what this expression is. My bounds match, so that's just going to be a width of 0, which means the area will be 0. I know slope comes from the derivative, so let's build the derivative function. And this is going to be applying second theorem because we're going to be trying to figure out the derivative of a function that has an integral notation in it. The derivative and integral will wipe each other out. The lower bound we ignore because that's just a constant. The upper bound will get inserted into the function, so we're just left with sine squared x. So now if we want to find derivative at x equals 4, just plug power, sorry, at power 4, plug power 4 into x. So that's really the same thing as saying sine of pi over 4 quantity squared. We know sine of pi over 4 is just root 2 over 2. We have our order pair, we have our slope. Put it all together, point slope form. All right, page 14. Sorry, this is answer choice D here. All right, the table above gives selected values for a twice differentiable function. Which of the following must be true? So we see these values from negative 130, go all the way up to 0, -2, goes up to order pair 310, and then continues to rise generally from from -1 to 5, from our y value of -30 to positive 18. It says f has no critical points on the interval from -1 to 5. And which of the following must be true? So from -1 to 5, it's definitely possible that there's a critical point from -1 to 5. We don't know. There's a lot of unknowns that we are unsure about with this graph, right? Here we can uh, see that. So critical point would be where the slope is either 0 or undefined, but um, uh, that could happen. But it also is possible that it may not happen either. Part B, f prime equals 8 for some value on the interval from -1 to 5. So basically, this is maybe getting us into that mean value theorem region here. If I can somehow show that there's a slope between -1 and 5 of slope of 8, then we must be able to guarantee there must be a rate of change of 8 somewhere as well. So typically, I like to start off with the endpoints. If I can I create and show that there's a slope of 8 between those two endpoints. So my average rate of change, slope between the two endpoints, is 18 minus -30 over 5 minus 1, 5 minus -1. Which is 48 over 6, which is 8. So my average rate of change is 8, and therefore, and it's a smooth curve, meaning that we can guarantee there must be an average instantaneous rate of change as well. So part answer choice B is an application of the mean value theorem. If there is an average rate of change of 8 between two endpoints, there must be a place where the slope is exactly 8. The other choices here, positive slope for all values between -1 and 5. Maybe that's the way that we graph it, but maybe the graph dips from 0 to 3 and we don't know about it because the table of values doesn't show us. So here, negative slope between 1 and 5, there's an average rate of change of negative from -1 to 5. Well, yeah, here it's asking about concavity. Okay, we don't know anything about concavity either because the graph could be changing directions that that we are unaware of between these points. So we can't guarantee C and D. And then the graph has no points of inflection. Again, there could be a lot of things happening between these points that we don't know about. So there's too many unknowns that is allowing us to predict those answer choices. So here's an example of what answer choice B could look like, because the two endpoints has an average rate of change of 8. Then the curve, maybe the curve looks like this, but if it's a smooth curve, there's got to be at least one point where the curve is experiencing that same slope as well. Okay, continuing on page 14, number 22. A particle moves along the x-axis so that at time t greater than or equal to 0, the acceleration is given by a of t. The position of the particle is 10 when t equals 0, when the position of the particle is 20 when t equals 1. What is the velocity of the particle at time t equals 0? So this is particle motion where we're given acceleration and we're trying to make our way up to the position function, and we're also asked about velocity. So let's gather some information here. All right, so what do we have here? We know the position is 10 when t equals 0. So there's an order pair here we can create. X of 0 equals 10. We also know that x of 1 is equal to 20. Okay, so let's work with the acceleration function and make our way up to velocity and position, and we can see how that can help us. So we know to get to velocity, we need to take the integral of our acceleration function. So I'm just going to get this ready for power roll. Okay, so apply power roll. We have data at the position level, so I'm going to keep going and make my way up to the position function. Now, we don't know what c is, but we do know that c is just a constant. And if I take the antiderivative, that constant will just become a linear. But if I take the antiderivative, another constant will show up. Flip that 5/2 to be 2/5. So now we have the position function. It's a general equation because we have all the c sub t, ct and c sub 2, but that's where these order pairs will come in handy. So I'm going to use these two order pairs to help me see if I can narrow down the c and c sub 2 that is unresolved. So if I'm just choosing which one to plug in first, I'm going to choose the one involving 0. That should wipe the terms out a little quicker for me. So I'm going to see what that 10 can help me solve. And if whatever c I can solve, I'm going to update that value and then use the second order pair to help me find the other c value. So I'll plug in 0 in for t and 10 for my position function. All my rest of my terms will zero out, and my c sub 2 is equal to 10. Let me update my position function with what I've just found. I'll plug that 10 in for that c sub 2 of my position function. So now the second order pair can help us out. 1 in for t, 20 in for x of t, and that should allow us to now narrow down to that c value. So I got c is equal to 6. Let me put that into my position function. So now the problem is asking, what is the velocity of the particle at time t equals 0? So now I'm going to just make my way down to velocity again. Now, if I plug 0 in, the only value that's left is 6. All right. 23. Which of the following is a solution to the differential equation? So now this is going to be a more traditional solving differential equation because your answer choices are all in terms of y. So we'll go through our steps, cross multiply. First order of business, trying to get that dy and dx's lined up. And now we have to find a way to get the variables to nicely be together on the same sides. So we want all the y's together on the left, everything, all the x's, everything else on the right. So we see one thing out of place here, x squared plus 1. We definitely want to get that to move. And then there's the y that needs to move as well. The 2, we want to make it stay. The 2 and the x, we want to make it stay. Just that y, we would like to move back over. So I'd like to do two things at once. So once we make that double substitution, now we have full separation of variables, and now we can explore integral rules. The left side is just natural log, right side, we do have to go through a little bit of use substitution there. Ends up being natural log as well on the right side. 1 over u du. Bring back our original variable. Okay, let me reset here. We took care of the integral on both sides. We raise both sides with e as the base. We know this becomes c. We know this will clean up to be just x squared plus 1. We can drag the c out in front. The plus or minus will be produced from, if I drop the absolute value, we get plus or minus, that comes out. If we drop the x squared plus 1's absolute value, a plus or minus will come out, and all the plus or minuses will just get moved into that c variable, that c value. Now let's figure out what that c value is. Order pair 0, 1. 0 in for x, 1 in for y. One is equal to c times 1, c is equal to 1. Okay, 24, page 15. Sand is deposited into a pile with a circular base. The volume is given by v equals r cubed over 3, where r is the radius of the base in feet. The circumference is increasing at a constant rate of 5 pi feet per hour. The circumference of the base is 8 pi feet. What is the rate of change of the volume of that pile in cubic feet per hour? So we have circumference of a circular base. So we have to understand that we're going to have to involve. And also here, the big picture here is there's all these mentions of time, rate of change with respect to time. So this is a related rates problem. And we kind of want to understand those steps here. As we find the derivative, we want our variable d over dt's to show up along the way. So the two equations that we're working with is r cubed over 3, or I can think of it as 1/3 r cubed. Let me just get the derivatives out of the way and just have everything in front of me. So c becomes dc dt. 2 pi r becomes 2 pi, r disappears, but we are asking for r's derivative with respect to time. So times dr dt. And then v's derivative right. What else do they give us? Circumference is increasing at a constant rate of 5 pi. So that's talking about dc dt. And the circumference of the base is 8 pi feet. What is the rate of change of the volume of the pile? So we're looking for dv over dt. Okay, so all right, so if I want to find dv dt, I have a formula for it. I just have to figure out two missing pieces, right? I need the r and I need the dr dt. Well, its circumference is 8 pi. I can use that to help me solve for r. And if I know dc dt is 5 pi, I can use that to help me solve for dr dt. So even though these are not variables and values that we need to get to dv dt explicitly, we do have a way to get to what we want to get to. All right, c equals 2 pi r. So plug in dc dt in for 5 pi. I can solve for dr dt. dr dt equals 5/2. So now everything that we need is in front of us. We have the r value. We have the dr dt value. So now that can help us solve for dv dt. Answer choice C. All right, 25. We're evaluating limit as we approach zero. So first thing is direct substitution first. So 0 in for h. This becomes e to the negative 1. E to the negative 1 minus e to the negative 1 is just going to be 0. 0 over 0 allows us to apply L'Hopital's rule. So e to the u becomes e to the u times u prime. E to the negative 1, that's just a number. So that number goes away to 0. And then h becomes 1. So now that we have a derivative version of what we started with, now we can just replace all the remaining h's with 0 and see if that will get us down to a real number. Before it was getting a 0 over 0. Now the hope is that this will give us a real number. And we get negative e to the negative 1, which is the same thing as negative 1 over e. And that matches with answer choice B. All right, number 26. Let f be the function given by x cubed plus 5x. For what value of x in the closed interval from 1 to 3 does the instantaneous rate of change equal the average rate of change? So that's basically f prime equaling f of b minus f of a over b minus a. It's basically the setup for mean value theorem. Okay, so my a and b values are 1 and 3. So we can figure that out by going through order pair. We'll find order pair, we'll find slope. F prime is just power rule. So we'll come back to that when we need it. But let's gather our order pair and find the slope between the two endpoints, right? Oops. 27 plus 15, 42. So our average rate of change. So we have our average rate of change. We have our derivative. We'll set them equal to each other and solve for x. Take the square roots, plus or minus. Now, in our plus or minus square roots, we are only looking for the C value that lives between the intervals. So the negative will be out. So our C value is going to be root 13 over root 3. Answer choice B. Uh, 27, if e to the xy minus y squared equals e minus 4, at x equals 1/2 and y equals 2, dy dx equals. So this is asking for derivative. Two things that stand out is there's a need for implicit because we see y variables mixed into our equation. And then there's also chain rule, e to the u becomes e to the u times u prime, but this is a little messier because that xy also requires a product rule within chain rule. So let me just remind us here, the derivative for e to the u is e to the u times u prime. So that means e to the xy will become e to the xy times u prime, and u prime is going to require us to evaluate the derivative of x and y connected to each other. So we have to worry about product rule to build out the derivative of xy. So this whole thing is my u prime. E to the u times u prime. Okay, so because of the u prime, we got to worry about think about the derivative of x and y. X becomes 1. Y stays the same as f stays. G is the same thing as y. F stays the same as x, and then g prime, y's derivative is my dy dx. Keep going. Power rule. Y squared becomes 2y dy dx. E goes to 0, 4 goes to 0. So I want to solve for dy dx. I find it easier, especially if they're not asking for us to find the derivative equation. If we can just go ahead and replace all of our x and y values at this stage, then things will clean up and collapse a little quicker and faster for us. So I'm going to just go ahead and do that. Plug in, replace. I already have my dy dx variable showing. So if I can just clean up, I could also solve for dy dx, but then that means we got to keep track of all these variables. So I'm going to just go ahead and plug in. So x gets replaced with 1/2, y becomes 2. Okay. Let me group my dy dx terms together. So subtract the 2e over. Now I just have to divide my parentheses over. So there's a complex fraction here. If I multiply the numerator and denominator by 2, I can get rid of that 1/2 in the denominator. One half e times 2 is just going to be e. And this doesn't quite match the answer choices that I have above. So we can always get to a different, quickly get to a different version of your answer by just multiplying the top and bottom by -1. See if that will produce one of the answer choices that you're hoping to see. Now I have 4e over -e plus 8. That's the same thing as 4e over 8 minus e. So answer choice C. All right, 28. Let f be the function defined by x cubed plus x squared plus x. Let g of x equals inverse of f, where g of 3 equals 1. What is the value of g prime of 3? So this is where we go through our derivative of inverse at a point. We go through our chart to kind of help map our progress here. So I'm looking for g prime of 3. I know that 3 is the x value of my g function, which must mean that 3 is the y value of my f function. So now we can just put all this into our function here. Oh, they do tell us that g of 3 equals 1. So g3 equals 1. That means that f of 1 must be equal to 3. Because of the order flip-flop order pair relationship. So now if I have f of 1 equals 3, if I can figure out what f prime of 1 is, then that will lead me to my answer. Okay, so let's see if we can work on finding f prime of 1. Before we can get to f prime of 1, we first have to get to f prime of x. So we go through power rule. After we find the derivative, plug 1 into the derivative. F prime of 1 equals 6. Therefore, g prime of 3 must be equal to the reciprocal. So 1/6. Okay, moving on to the calculator section. The graph of function f is shown. Which of the following limit does not exist? So limit not existing is if I can pick points on either side of my target and they're not headed towards the same y value. So 3 is a good candidate because if I pick points on either side of 3, one side is headed towards a y value of 2, the other is headed towards a y value of -infinity. The arrows are not matching up. They're not pointing to the same destination, so therefore limit doesn't exist. Next up, page 17, continuing with page 17, number 77. Let f be a function that is continuous on the closed interval from 1 to 3, so no breaks, no holes. F of 1 equals 10, f of 3 equals 18. Which of the following statement must be true? So let me just draw this graph out. So let's say f of 1 is 10, and f of 3 equals 18, and my graph has to connect between those 2 points. Can we guarantee that f of 2 is between 10 and 18? Maybe, but it's also possible that f of 2 could rise above or go below. So we can't guarantee, I mean, the way that we drew it, f of 2 is between 10 and 18, but f of 2 doesn't have to be a point between. So we can't guarantee this. F is increasing from 1 to 3. That is the way that I drew it, but all we know is that these are the endpoints and the graph is continuous. We don't know that the graph is going to just going to be rising the whole way. Okay, f of x equals 17 for at least one solution on the interval from 1 to 3. This one is true, right? Because if the graph is going to connect from a y value of 10 to a y value of 18, it has to pass through that y value of 17 at least once. F prime has at least one solution. F prime equals 8. We can't guarantee a slope of 8 because it's continuous, but it doesn't indicate that it's differentiable. So if I want to guarantee anything about slope, I need some conditions about differentiable as well. And then it says the area from 1 to 3 is greater than 20. We don't know what the shape of the graph is like. We can't guarantee that this is any value less than or greater than a known value. So answer choice C is the only one that we can guarantee. That's IBT. Page 18. Let R be the region bounded by the graph of y equals x cubed, y equals e to the x, y equals e to the cubed, and x equals 0. Which of the following gives the volume formed by revolving R about the line y equals -1? So y equals e to the x is an exponential graph that looks like this. Y equals e cubed is just some, think of e as around 2.7 or like 3-ish. So we know that it's just somewhere close to 8 or 9. It's just going to be some horizontal line, right? E cubed is just some decimal number. So let's just call this line e cubed. And the y-axis. So here's our shaded region. Okay? Which of the following gives a volume rotating about the line y equals -1? You see the word revolving, rotating. You know it's either disk or washer. So let's look at our dotted line down at -1. Now we can see that there's obviously a gap. Even if it was touching the curve, there's not going to be closed. There's going to be some gaps. So only we're going to rely on washer method. So we extend our dotted line to the furthest boundary. That's going to be your big radius. From the dotted line to the closer boundary, that's going to be your small radius. Now let's build our big R and little r. Okay, big radius, top minus bottom. Top of my big radius sitting at the e cubed. Bottom of my big radius sitting at the -1. So I can just subtract that. Small radius. Top is sitting on the e to the x. Bottom is sitting at the -1 still. So e to the cube plus 1 is my big R. little r is e to the x plus 1. Now we just put it into our volume formula for washer method. Big radius quantity squared minus little radius quantity squared. And we're extending from 0 to whatever this x value is. And that's the intersection between e cubed and e to the x. And that's just going to be 3, right? If I were to plug 3 into the x, or e cubed in for y, I can match up the fact that that x value must be 3. All right, 79. The number of people who've entered the museum on a certain day is modeled by the function f of t, where t is measured in hours since the museum opened that day. The number of people who have left the museum since it opened, same day, is modeled by g of t. If f prime is given and g prime is given, at what time is the number of people going to be at a maximum? So the maximum is going to occur whenever my f prime is equal to g prime, right? Where my critical points are going to match up, right? Or if I were to subtract the f prime minus g prime, and I'm able to get that critical point to be 0. So now I can just put this in the calculator, make this y sub 1, make this y sub 2, and then subtract y sub 1 minus y sub 2 in your calculator and look for the x-intercept. You're going to want to adjust your x-min and x-max to be 1 and 11. And then you also want your y-min, y-max to be up in the hundreds. So let's do like negative 300, 300. And then you can graph and then look for the x-intercept. Okay, in the interest of time, I'm going to just continue with the rest of these problems here. So next up, page 19 or 18. Derivative of a function f is continuous. Values of f and f prime are given. If the definite integral from 0 to 4 of f prime is 8, then f of 4 equals. So I like to rely on this final equals initial plus displacement to kind of give me a framework for this problem here. So I'm looking for f of 4, or I'm looking for f of 4. I have f of 0, which I can pull from the table. And then the integral from 0 to 4 of f prime, they tell us, is 8. So end position equals initial plus displacement. If I can get into this form, then I can just plug these in and solve for f of 4. Next up, 19. A slow field for a differential equation as shown in the figure above. If y equals f of x is the particular solution to the differential equation, then h prime of negative 1 equals. So if I want to find h prime of negative 1, I first have to build out h prime of x. To get to h prime of x, I'll have to go through, in this case, product rule, because 3x times f of x. So f prime g plus fg prime. So 3x becomes 3. We keep the g function, back to the f function, and then f prime. Replace all the x's with negative 1. And so f of negative 1, we can pull this from our graph here. F of negative 1 is 2. They give us that order pair. f prime of -1, we can just pull that from the slope field. So f prime of -1, the slope here, all these slopes are in agreements. Or negative, sorry, at -1, 2, my slope here is -2, because I could just pick any points here and go down 2 over 1. So that's a slope of -2. So slope of -2 will replace my f prime of -1. And now I'm just trying to combine these values to get it down to a number. Answer choice E, which is 12. If f is a continuous function such that f of 2 equals 6, which of the following statements must be true? We can just make a substitution here. F of 2 is 6, and the limit of 6 squared equals 36. Particle moves along a straight line given by v of t. What is the acceleration? So you have velocity. To get from velocity to acceleration, we can just do math 8. You can do math 8 and plug in 4 into the velocity, into acceleration. Or I think this, you can also work this out by hand. This one's not too bad because e to the u becomes e to the u times u prime. You can plug 4 into this e to the u times u prime, and you'll get 1.26. But you can also do math 8 off of the velocity function and plug 4 in. Since this is calculator, you'll get that same answer. 84, a home uses fuel at a rate of R of t. To the nearest gallon, what is the total amount of fuel oil used? So we want to get from a rate up to the function level. We just take the antiderivative from 0 to 6. So this is quick. Math 9 will give us that answer. Page 20, f prime is given, and we just put it in the calculator. Which of the following statements is true? So understand we're trying to interpret an f prime graph. So if we're interpreting an f prime graph, then we know that any x-intercepts will be places where your slope is 0. Above is positive slope of the original function. Below is negative slope. So I'm just going to create an f prime sign line here. And then I know the peaks and valleys of my f prime, the max and mins, will be the points of inflections of my original function. So there is a point of inflection at 1.25. If I do second trace and pick a max, pick points on either side of my relative max, it'll get me to that 1.25. And there's a relative min at 2.17. Positive slope means concave up. Negative slope means concave down. Positive slope means concave up. So if I can have this slope and concavity sign line in front of me, I can narrow down my choices a lot quicker. Relative max from, there's relative max from 0.4 to 2.4. That is definitely true. There's a relative min from 0.4 to 2.4. There's no relative min because we would need a decreasing followed by an increasing. 2 points of inflections. We do see 2 points of inflection. Concave up to concave down, that's 1 point of inflection. Concave down to concave up, another point of inflection. So answer choice D. All right, 86. The graph of the function f has domain from 0 to 7, as shown in the figure. The graph consists of a quarter circle, a radius 3, and a segment with slope of -1. Let b be a positive number such that the depth integral from 0 to b is equal to 0. So we know the area from 0 to b is going to cancel out to be 0. What is the value of b? So we want to find the b value such that it will allow the area of the quarter circle to match the region below the x-axis. So we basically want these regions to be able to cancel out. So we know the depth integral from 3 to b is going to be under this graph here, this graph that we can imagine here. This has a slope of -1. It goes through that order pair of 0, 3, of y-intercept of 0, 3. We can create that tangent, that line to be -1x plus 3. So we want the area of the quarter circle to match the region of the triangle below the x-axis. Right. And we know the quarter circle here is 7.0685. So we take the depth integral here from 3 to b. We can go through power rule here, and we can get that -0.70685. And now we can just bring everything over to one side and graph this and look for the x-intercept, and that can help us get to that b value. Okay. Page 21, number 87. G prime graph is given to a curve is given to you. If we put that in the calculator, we're looking to see where is the G graph decreasing. So G graph decreasing would be where, sorry, I meant to write G prime here. We're looking for regions below the x-axis. So wherever the G prime graph is below the x-axis, that's where my original G graph is going to be experiencing negative slope. So we graph it. We do find x-intercepts by doing second trace 0, and we get 0.7 and 1.2. The height above the ground of a passenger in a Ferris wheel, t minutes after the ride begins, is modeled by a differentiable function. Which of the following is the interpretation of the statement h prime of 7.5 equals 15.7? So this is basically his rate is increasing, or his the rate of change of his height is changing by 15.708 meters per minute at this moment in time, 7.5 minutes after the ride begins. '89, the particle moves along a straight line. Velocity is provided by our graph here. What's the total distance that the particle travels? So every region, as long as we consider every region positive, then that's going to be total distance traveled. So even though he's moving backwards or to the left, if we just count everything as positives, then that will give us total distance. So I have a square here, which is 4, triangle here, 1/2 base times height, triangle here, 1/2, square, which is the area of 1. So I add those together, I get 6.5. All right, let f be a twice differentiable function. If f prime is positive, that means positive slope. Greater than 0 means positive slope. And f double prime is negative, which could be a graph of f. So we want a graph that has positive slope and concave down. Pair those two together. The only graph that's going to experience that is answer choice C. Positive slope rising from left to right, concave down. It has that portion of the, looks like a portion of a parabola opening down. The graphs of f and g are above. Find h prime of 6. To get to h prime of 6, we have to see how our h of x is designed. It's designed as with two functions being multiplied. So we got to go through product rule. F prime g plus fg prime, replace every x with 6. And now we're just pulling data from our graph. Either we're pulling the order pair of our f and g, or we're pulling the slope of our f and g at that point. So at 6, my order pair for f is 2. My g graph has a y value of, f graph has a y value of 2. G graph has a y value of 4. F graph has a slope of -2 because I just picked 2 points here, down 2 over 1. F graph has a slope of -1/2 because I can just pick 2 points here and go down 1 over 2 and just put it all in, get my h prime. All right, last one here. In the xy plane, the graph of differential function is concave up on the open interval. Which of the following statements must be true about the derivative of f? So we know our graph is concave up, which means that our curve will just continually increase in slope. Now we know that there's a tangent to the graph at 1, which is 3x minus 2. So we know that this graph is experiencing a slope of 3. If this graph is experiencing a slope of 3, then that means anything to the right will have to be greater than the slope of 3. Anything to the left will be less than slope of 3 because our graph is maintaining that concave up. So f prime of x is going to be less than or equal to 3 on the interval from 0.9 to 1. Since the graph is concave up, slope of the curve is still increasing. So slightly to the left of x equals 1, the slope must be less than 3, because if it's concave up, my slope will continually increase. So that means to the right will be greater than slope of 3, to the left will be less than slope of 3. So answer choice A. Okay, at this time, I'd like to move into the BC test. So I'm going to just pick out problems from that BC multiple choice test, or I can field any questions that you guys have. But I'm going to stop the recording now and then start a new one for the BC.